recorder. So now it's recording. All right, so I'm going to go over the relations homework first, and then we'll proceed to talk about propositional logic. So there we go. I think the mic is good. And all right. All right. So here's the relation homework. And I'm going to do this one by one, just like you guys did. There we go. All right. All right, so question number one is consider the not equal to relation over all integers. Which of the following relation properties apply? So you basically just have to check the ones that apply and do not check the ones that do not apply. All right, so partially ordered, that we don't know yet. Okay, so we're gonna have to check out the three requirements for partial ordering, and then we can decide whether to check that box or not. Transitive is one of those, and inequality or not equal to is not transitive because you can choose the values of 1, 2, and 1. 1 does not equal to 2, 2 does not equal to 1, but 1 does equal to 1. Okay, so transitive does not apply in this case. So we don't want to check transitive, which also means partial order is out already because transitive is one of the properties that you need in order for a relation to be partially ordered. So we know the first two, definitely know, and then the third one is even easier because if it's not partially ordered, it cannot be totally ordered. So the first three are gone completely. Is it symmetric? The answer is yes, it is symmetric. If A does not equal to B, then B does not equal to A, and vice versa. So symmetric is working. Is it reflexive? If you choose any value, is it not equal to itself? Nope. So transitive, reflexive has to be no. And then anti-symmetric, I think this one is pretty easy. Is it anti-symmetric? Is the not equal to relationship not is it anti-symmetric or not? It is not anti-symmetric because in order for two things to be related by not equal to, they have to be not equal to each other. And because it is also symmetric, so if you choose two values, A and B, such that A does not equal to B, then B does not equal to A automatically. But that also means A and B cannot be the same because of the way not equal to works. So not anti-symmetric is also going to be not true in this case. Are we good so far? Moving on to question number 2, which is equal to this time. So I'm just going to pick symmetric because equal to, if A equals to B, then B equals to A. Okay, that is pretty natural. And then transitive, yes, it is also transitive because if A equals to B and B equals to C, then A equals to C. Well, that's got to be true because A, B, and C, they all have to be exactly the same anyway, right? So it is also transitive. We cannot quite answer partially ordered at this point because we need to know whether it is also anti-symmetric. It is anti-symmetric because the only time when you have A relating to B, B is also related to A in this case, is when A and B are exactly the same. So does that imply A and B are the same? Yep. So anti-symmetric is also true, which also means it is partially ordered. So we can check this box right away. Is it reflexive? It is reflexive. Actually, okay, I checked that box a little too early because you also need reflexive in order to be partially ordered, but reflexive is true because every value is equaling to itself. So it is reflexive. And the last one is it totally ordered? The answer is no, it is not totally ordered because equal to cannot relate, let's say 1, 2. So does 1 equal to 2? No. Does 2 equal to 1? No. So that means in that particular case, the relation does not work one way or the other, which is basically the last requirement that we need in order for a relation to be totally ordered. If you have any questions, during, the discussion, just kind of let me know, and we can work on it. You can give me an example, and then we can work it out. Question number 3. R and S are both relations defined over X, and we also know that the intersection between R and S is reflexive. Then what do we know for sure about R? Well, R and S are both relations, and we know that R and S is reflexive. So that means R by itself has to be reflexive. But that's the only thing we know. Are there any questions about this one? Because this one does bring us back to the set operators. Because if the intersection between two sets by itself, has certain elements, that means those elements have to be present in both of those sets. In this case, R and S. Does that make sense? Okay. And we only need the AA, BB, CC, and so on, in order for a relation to be reflexive. Question number 4. Consider the less than relation over integers. Which of the following relation properties apply? It is certainly not reflexive because the value is not less than itself. So reflexive is out, which also means partially ordered is out also automatically, which also means totally ordered is also out automatically. It is not symmetric because 1 is less than 2, but 2 is not less than 1. So it is not symmetric. It is transitive because if A is less than B and B is less than C, then A is less than C. That makes sense. I think, okay, we only have anti-symmetric left. And anti-symmetric is going to be true. Why? Because you cannot find the conjunction on the left-hand side of the implication to be true. Because if you given any two values, okay, A and B, I don't really care which one you pick, you cannot say A is less than B and B is less than A. That simply cannot happen. So that means the conjunction on the left-hand side of the implication has to be false, which also means the implication itself has to be true. It doesn't even matter how you choose your A and B. For every single way you choose A and B, the conjunction has to be false. Is that okay? So that is why it is anti-symmetric, because if the left-hand side is false all the time, for the implication, then the value of the implication has to be true. Question number 5. Consider the greater than or equal to relation over integers. This one, check every box. Because, okay, let's look at it. If I give you if I give you this relation greater than or equal to, is it reflexive? Is a value greater than or equal to itself? Okay. Is it transitive? If A is greater than or equal to B and B is greater than or equal to C, does that imply A is greater than or equal to C? Yeah, seems to make sense. Is it anti-symmetric? It is anti-symmetric because if you give me two values, if A is greater than or equal to B and B is greater than or equal to A, then A and B must be the same. But it can happen. So the implication that A and B are the same when A relates to B and B relates to A is true. That implication is true. So it is anti-symmetric. It is not symmetric. So I said, what I said earlier was wrong. We cannot check every single box because symmetric is not correct. If I choose A to be 1 and B to be 2, then it is not symmetric because 1 is less than the other way around. 2 is greater than or equal to 1, but 1 is not greater than or equal to 2, so it is not symmetric. But it is partially ordered because partial ordering does not rely on symmetry. And it is also totally ordered because if you choose any two value, okay, they are related one way or another. In other words, pick me two values. I can say one is greater than or equal to the other one. Okay, and that's why it is also totally ordered. Any questions about number 5?
Would less than or equal to have the same properties?
Yep. Less than or equal to would be totally ordered as well. All right, number 6. If R is a relation defined over X is known to be reflexive, which of the following do we know for sure, regardless of the actual definitions of R and X? All right, so we will reserve the first one until we confirm none of the other ones can be confirmed. So we'll check it out. The cardinality of R has to be greater than or equal to the cardinality of X. I think so, right? Because every element of X has to relate to itself. So that means we need at least as many elements as there are in X in R. Okay, think about a small example. Let's just say that X has A, B, C. That means R has to have AA, BB, CC. It can have other things, but AA, BB, CC are guaranteed. So that means we kind of know this one is we can potentially check this one, but we'll also check the other ones to make sure that I did not write the question incorrectly. Okay, do they have to be the same? Do the cardinalities of R and X have to be the same? No, R can contain additional stuff. Okay, you can add some stuff to R, as long as it is still reflexive. It can have more elements than the number of elements in X. It cannot be less. Okay, so we know this one is definitely not true. Do they have to be different? No, they can be the same, exactly the same. So the correct answer is the second option, at least in my test over here. And then for question number 7, R is a relation defined over X, and R is known to be symmetric this time. Which of the following do we know for sure, regardless of how R and X are defined? Hmm. Well, this one is kind of interesting, so we're going to have to evaluate all of these and find out which one applies. Do we know for sure that the cardinality of R is less than the cardinality of X, just because we know R is symmetric? The answer is okay. How do we answer these questions? What did you guys do to answer these questions? You come up with a small example. Okay, don't try to pick an X that has like 100 elements. That's going to kill you. Pick two. Okay, one is a little bit too specialized, or no elements is a little bit too specialized. So we don't want to necessarily use cases that are too simple. So if you just choose two elements, you can basically say, if I just define every single possible relation, in two elements, so let's just say X has A and B in it. Then R, having every single way of relating everything, is gonna have AA, AB, BA, and BB. That's four elements, and four is more than two. So that means we know the first one that cannot be the right answer. And that also, now let's look at the second answer, okay, which is the cardinality of R cannot be the same as the cardinality of X. It can be, because anything that is just reflexive is also symmetric. And if it is just reflexive, then the cardinalities of the two have to be exactly the same. So we know it cannot be the second one. The third one is also not true because they don't have to be the same. They can be different. Because an empty relation is automatically symmetric and it has 0 elements in it. All right, we skip this one until we confirm all of the other ones cannot be the case. So this one says the cardinality of R has to be even. That is not true. If you have AB in X, then you can have just AA in R. It will still be symmetric, right? So we can rule out even. We can rule out odd too, okay? Because remember the empty relation, the empty set has 0 elements. 0 is an even number. So now we can also rule out odd. So we only got these two left. Um, Let me point to which one we're talking about. This one here. It doesn't have to be greater than because we just used the empty relation as an example. The cardinality of an empty relation is 0. Okay. And it doesn't have to be exactly twice, okay? Because if we know that the cardinality of R doesn't have to be even, that kind of rules out this one already, right? So The answer is actually none of the other choices can be confirmed. So pick that one. And we have one more, or how many more questions do we have? Oh, that's it. 7 questions. And let's see. Let me see if I get all the points. Yep, I got 7 out of 7. Are there any specific questions about this assignment? No? All right. Well, if there are no questions, then we are going to move on because we got a pretty long module. Not going to be done in one class for sure. Maybe 3-ish, classes, for this one. All right. And you can see there's a bunch of prerequisites to this particular module, which means it might be helpful to kind of click on these links just to make sure that we understand all the definitions and all the symbols and all the concepts from these 4 earlier modules. All right, so propositional logic is nothing new. Okay, it has been around for a long, long time. The Greeks, first came up with propositional logic a long time ago. It applies to arguments, for people, they want to apply logic when they, argue, and so this is nothing new. Um, but what we're going to do here is we're going to have a spin of automatic program verification. Automatic program verification is basically, if I want to describe it, very vaguely, okay, in general, is you are given a program. Okay, let's just say you have a program written in C, and you have a description of what the program is supposed to do. If this is the input, that that condition over there needs to be true when the program exits. So you're describing the expected behavior of a program using mathematical symbols and statements and whatnot. So the question is, well, does it meet those requirements? Without automatic program verification, how do you do it? Let's just say that 10 years from now, you guys are working as a developer or a software engineer at a company. And then your boss says, last time we released, something, we got a lot of bugs and, it was not good. Okay, bad for the reputation of the company, bad for the clients, and so on. So what do you do to make sure that the program does, quote unquote, work correctly?
Well, test it
Test it. Okay, very good. But how do you test it?
by trying everything out, making sure it works.
Okay, so that is one way to do it, but in reality, you cannot do that. There are too many possible ways for input. So let's just say that you're writing string compare. Okay, string compare is a really simple little function, right? All it wants to do is to see if one string is less than, equal to, or greater than the other string, and come back with the right answer. Okay, but how do you enumerate all of the possible ways, all the possible two strings to be compared? Because that would be the right way to prove it, right? To use a test to prove everything. Because if you say, well, I tested like 20,000 pairs of strings and it seems to be working. Well, what is telling you that the 20,001st pair of string is also going to work? There's no guarantee, right? All you can say is it does work for these, but we have no idea whether the next test case is going to work or not. So when it is a technique that we do use these days, and we get a pretty good feel that, yeah, if it works for empty string compared to empty string, non-empty string to empty string, this string to a non-empty string, and so on, you test for the boundary cases, you get a pretty good feel that it probably is going to work, but we never really get a 100% confirmation. Automated or automatic program verification is basically letting a computer to do all the math for you. So we are mathematically doing it step by step to basically show that if this is the initial condition and this is the code, by the time we get to the end of this entire program or algorithm, this condition is guaranteed. That's automated program verification. It really has nothing to do with programming. It has everything to do with math and logic. Okay? So it'll be great if we can do that, because then we can basically look at least core portions of an operating system and say this part here cannot go wrong. Okay? There are certain key portions of an operating system that are of particular importance to reliability and also cybersecurity. To understand the issue of not having automatic program verification, you only have to go to Heartbleed as a security problem. So if you go to Heartbleed, which describes a bug in the SSL TLS library, it's a software problem. Okay, somebody wrote the program, did not really quite check every single condition, and it turned out to be possible for someone to ping a server, and you can potentially get the certificate, the private key back, which is bad. Okay, so you can read the rest here on your own. Okay, but the point is, it is a bug, it is a flaw in the software, but the consequence was really big. Okay, it has a lot of implications when it comes to cybersecurity. if if what we talk about here is reality, that would not happen. That would not have happened. Is that okay? Now, cybersecurity, well, I'm just going to segue a little bit to talk about the importance of cybersecurity. Um, it has always been quote unquote important, but back in the old days, when most companies do not even have a constant internet connection to the internet because internet does not exist, cybersecurity was not really that big of a deal because the only way to spread a virus is by floppy disk. Some of you are young enough to 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 to, to listen to the words floppy disk and going, what is that? Right? I mean, some of you are probably old enough to remember what a floppy disk is, but basically, in order to transmit a virus from one computer to another computer, a person needs to physically get the disk on one computer, save a file, and the file is infected, walk over to another computer, put the floppy disk in, and guess what? It doesn't run by itself either. You actually have to run a command or open the file in an application program in order for the other computer to be infected. So think about the speed of how fast this virus can spread. Not very fast, right? Think about the fan out ratio, okay, from one computer. Once one computer is infected, how many other computers can also be infected in one single hop? Not too many, because it's limited by access to the computer. I mean, back in those days, only one person can use one computer at a time. So everything is very sequential, very linear. So cybersecurity was a concern, but it's not like super duper important because in order for something to spread all over, it's not going to be that fast. These days, it's entirely different, right? One vector, one way, to infect computers was to find a way to embed something into an image, and just by a browser opening the image can infect a computer. That has happened before, and it just happened, I think, maybe a few months ago. Somebody figured out a way to put a payload of a virus into an image. I'm talking about a PNG or JPEG or something along that line, nothing exotic. So just imagine you post an ad, somebody posts an ad on eBay and say, oh, this is a great gaming computer and it's super duper inexpensive. Everybody wants to click on it, go like, oh, I want to take a picture of the computer, what's inside, what is the condition, what graphics card is inside, and so on and so forth. Just by clicking, just by the image loading in the browser, a computer can be infected. Just think about the fan out ratio, okay, because of eBay, Etsy, of all of those websites. The fan out is insane. Okay, it can spread really, really quickly. Okay, so what? A computer is infected. Back in the old days, when Microsoft Word is infected or when the PC is infected, potentially you lose your data. You get a screen, showing that yes, I just infected your computer. Ha ha. Okay, and that's kind of the worst thing that can happen is you lose everything on that computer. And that's back in the days when the entire computer has a hard drive capacity of 20 megabytes. Yes, you're going to lose 20 megabytes worth of content at the most. These days, what can happen?
You get to all your safe passwords. It can go through and just track you. There's so much stuff that you can do.
There's a lot of stuff that's just from the end user's perspective, right? Think about the power grid. The power grid is getting automated. It's going to be controlled by programs. So that means to shut down the power grid, potentially, someone doesn't even need to get close to actually a transmission tower or line or generator because they can do it remotely. So the implications of cybersecurity is a lot more than, say, 20 years ago or even just 10 years ago. I was watching a YouTube video of how all the major countries in the world, they're all developing Gen 6 of fighter jets. So you might think, oh, Gen 6 fighter jets just faster, maybe, can have a longer range, and that's about it. Well, yes, all of those things. But in addition, every single country is developing drones to help out here with an actual piloted aircraft, and they're also testing how they can use drones to do aerial combat, and they found that in simulation the drones or the AI can learn techniques that were not discovered by pilots. So professional fighter pilots with years and years of experience did not find a way of how to strategize the flight pattern, but the AI did. So if you think about the implications of what is the result of a computer system getting infected, and somebody else is gaining control of that computer system, the consequences of that happening these days is very far-reaching. Um, and that's why I want to kind of emphasize that, because if you think that this stuff here, this boring, dry stuff that we talk about here, it's just dry and boring, it has nowhere to go. Well, that may not be the case. Okay, if you want to really get into computer security, cybersecurity, and you want to double check and make sure that operating systems are written correctly, so the chances of getting infected should be zero, this may have something to do with it. Okay, now this is equivalent to an undergraduate lower division class at a four-year university. So this by itself is not going to be the answer to the questions that I asked earlier. But this is one step to those other classes that you might need to take. So I just want to make sure that there's context to understanding this material. All right, so we are now back to the dry and boring stuff. General propositional logic. There are 5 components to a propositional logic system. Okay, so we're talking about a system over here. These are all Greek letters. This is uppercase alpha. So alpha is a set of symbols to be used. Each symbol or each item in this set has no specific inherent meanings. So just a bunch of symbols. They're usually single letters. And then we have omega. Omega is a set of operators, otherwise known as connectives. Connectives connect symbols and the result of connectives. So I'll give you examples later on. So these kind of abstract description will become more clear in just a little bit. Omega can be broken up into subsets, where omega I determines the number of items connected by a connective. So omega 2 is going to be all the connectives or operators that connect exactly 2 items. From our perspective, in layman's term, omega 2 are the basically the binary operators. Binary in this case is not 0 and 1. It means it has two things that it needs to work on. So multiplication is a binary operator, and is a binary operator, or is a binary operator, but negation is not. Negation only takes one thing, so it's a unary operator. So that would belong to omega 0, omega 1 in that case. So it's just technicality that we can break it up into multiple subsets where it depends on how many operands each operator requires. Zeta, okay? Zeta is a set of transformation rules. So we'll talk about this later, okay? Because we can't really talk about transformation rules until we know what exactly is a well-formed formula. So we'll defer the discussion of zeta, and because we have not really talked about what is a well-formed formula, iota really cannot be talked about in details. But basically, iota is the seed of the entire thing. Everything that is known to be true is in iota. Okay. Okay. So the next thing is what exactly is a well-formed formula, or WFF? So I'm using these definitions here because I want to reuse the quantified expressions as much as I can. So this way, by the end of this entire semester, you guys can look at this and go like, yeah, we know exactly what that means, because you'll be used to it. Hopefully, you'll be used to it even now instead of at the end of the semester. But we'll see. All right, so I'll just go ahead and read each one out here one by one, and then give you the meaning of each particular statement. So the first one says every element in alpha is a well-formed formula. It is an assertion. It's basically saying if you take any single element out of alpha, that by itself is considered to be a well-formed formula. Are we good so far? Okay? All right. So that's the easy one. The next one is recursive. So that makes it a little bit interesting. So the second one says, as long as I is in 1 to n, this is just a range of value. If I know that phi I is a well-formed formula, and C is in omega n, this is the connective, and it takes n components to the operator, that implies if you apply the connective C, which requires exactly n operands, and you give it each operand is a well-formed formula to begin with, then C of phi 1 all the way up to phi n is also going to be well-formed. It is a recursive definition of what is well-formed. Yep.
What is alpha? Like, can you give an example of what alpha?
Yep. We'll get to that point at some point. But right now, this is just a recursive way of doing it. Okay. I think it makes sense to use an example right now. So we'll go ahead and take a look at some examples. I can type it really neatly if I use Joplin, but it's going to take me longer, and it's going to look more confusing because you guys will have to kind of look at the unfinished formulae as I work on it. So I'm just going to handwrite everything. This is from the previous class. I'm going to add new page after. Okay, there we go. And then we'll go ahead and use a concrete example. All right, so the first thing is we want to define alpha. So I just want to give you an idea of what a typical alpha may look like. So I'll put 0 here and 1 here. But remember, these are just symbols. 0 has no meaning on its own, 1 has no meaning on its own. It is simply a symbol. That's it. Okay? And then I'll use English alphabet letters like P, Q, R, as the names of variables. Once again, they are just symbols, okay? If you say, I don't like P, Q, and R, I prefer my variables to be X, Y, and Z, okay? Well, be my guest, okay? Because all we're trying to do is to say, okay, these are the symbols that we're dealing with, okay? And if you want to choose some other alphabet, that's fine too. Okay, but in this class, I'm just going to say choose a P, Q, R, S, T as the names of what we call variables. Okay, and typically you also have some Greek letters in it. I think omega is 1, so omega is in lowercase. Okay, rho first. Okay, so we have rho, phi, and omega. What is omega in? No, no, no. We don't use omega. We use theta. There we go. There we go. Okay. So generally speaking, there are three categories of symbols. Okay. These two are constants. These three are variables. These three are usually called schemata. Okay. So right now, those terms make no sense. Okay. So we'll get to the point where they will start to make some sense. Okay. But right now, these are just symbols. They're nothing more than just symbols. They have no intrinsic meanings whatsoever. So that's the first thing. The second set are the omegas. So we are going to model normal logic. So omega is going to have the operators that we know. So we'll say it's omega 2 union with omega 1. And then omega 2 is going to have all the binary operators that we are used to. Okay, so it's going to have conjunction, disjunction, implication, if and only if, or equivalence. And I think those four are the most used ones. And then omega 1, which is the set of unary operators, will just have negation. Okay? So we are now defining omega to resemble what we use to deal with logic. When we express logic, we use these operators. Okay? Are we good so far? I think this is all we need in order to explain what is well-formed. So if I want to give you a set of well-formed formulae, okay, um, it's actually explained later in the notes too, but I'm going to give you some examples, okay? So if I just look at this, is it well-formed? Well, if it is, why do you think it is well-formed based on the definition of what is well-formed?
Because it's in A.
Because it's in alpha, okay? It's one of the alphabets, okay, in alpha. Okay, so this is a well-formed formula. Okay, very good. Um, let's pick something else, okay? Let's pick P or Q. Is that well-formed? If it is, why is it well-formed? How do you connect the answer to the question of whether P or Q is well-formed to the definition of what is well-formed? So the answer to the first part of the question is yes, it is well-formed. But the second part is asking, why is it well-formed? Well, just because it looks good. No, we want to connect to the exact definition of what is well-formed. First of all, does it have an operator? Okay, it has an operator, which is the OR operator. And which omega set does it belong to? It belongs to omega 2, which means the OR operator needs two things in order to operate, right? So now we look at each thing that we gave it to operate on. One is P and one is Q. Is P well-formed by itself? Is P itself a well-formed formula? Yes, because it is found in alpha. Same thing applies to Q, right? So that is the reason why P or Q is also a well-formed formula. Okay, so now we'll say is a well-formed formula. All right, so let's take a look at R. Okay, so R is a well-formed formula because R is an element of alpha, and every single element by itself from alpha is automatically a well-formed formula. So we got that. So now we look at some silly stuff, okay, some stupid stuff. So we'll ask, what is R and R? Is that well-formed? But tech, that's just R itself, because we understand the semantic of and that's just R. But remember, when you look at these symbols and these symbols over here, they have no inherent meanings whatsoever. We are looking at kind of like a compiler perspective, okay? Is it syntactically correct? That is the only question. Is it syntactically correct? Okay, we are not looking at runtime behavior, does it do something useful or not? We're just looking at syntactic correctness. Okay? So if R and R itself is well formed, and we just need two well formed formulae for and to become well formed, so now we can say, what about this? R and R and R and R. Well, that is well formed, right? Because we just showed that R and R by itself is well formed. So now we have two well-formed formulae as components to an and, which is from omega 2. So that makes the and expression itself also well-formed. But is it useful? No, absolutely not useful. But we are not talking about semantics. We are not talking about is it useful. We're simply asking, is it well-formed? So well-formed means syntactically correct. That's all it means. Are we good so far? All right. So now we can move on, in the browser, and then we can now start to talk about the other things that we need to talk about. So we'll start with iota. So this is you can say I, okay, but I'm going to call it iota. It's the uppercase of the iota Greek letter. This is a set of well-formed formulae that are known to be true. In other words, they're axiomatic. You don't question why they are true. They're simply given to you as expressions that are true to begin with. Is that okay? Because you have to start somewhere, okay? If you want to argue with somebody about something, the two people who are arguing, they have to agree on certain facts that are commonly understood as true. Because otherwise, there's no need to argue, because they're going to go like this in terms of the argument. Is that okay? So iota is simply things that are given to be true, okay? You do not ask why that is true. So I can, as an example, okay, let me switch back to Zerno. So as an example, I can give you an iota that has one as a single, as a well-formed formula. Are we sure this is well-formed? Yeah, we are pretty sure because one is in alpha. Okay, so this is how I associate quote unquote semantics to the symbols. Okay, is starting with iota. So I can also say that is given to be true. Kind of makes sense, right? The negation of false is true. Okay, so we are basically choosing things so that it resembles the logic system that we are used to. Now, does that mean that you can do something else? Yeah, absolutely. It's just that you might end up with a logic system that has no um, that is not sound. In other words, it makes no sense. It has no application, when we're trying to use it. Okay, so I'm specifically using one that makes sense. Okay, and you can then say, P implies Q is known to be true. Now, why? I don't know. I don't care. Okay, it is just given to you as an axiom that P implies Q by itself is first, it is well formed, right? And two, it is true. Why is it true? We don't know. We don't care. You can also add some other stuff like not Q or R, okay? So that is also given to you as true. So we'll just kind of go ahead and say this is it, okay? This is iota. This is everything that is known to be true. What are we going to do with it? Well, before we talk about what are we going to do with it, let's talk about the set of all well-formed formulae. Okay? I'll give you an example. I can start. Okay, so let's say uppercase W is the set of all the well-formed formulae. So we know, where we can start. Okay, we'll copy everything from alpha, 0, 1, P, Q, R. The Greek letters are kind of funny. They really should not be part of it. Okay, I'll explain why that is the case. And then we can say, oh, okay, if these things are all well formed, so is R and R, so is R and R, and R and R, and so on. Okay. The first question is, how many elements are in W? I just need one of two answers. Is it finite or is it infinite? I think this gives you an insight into the conclusion of it is infinite. Because I can stack this infinitely and it will still be well formed. It's silly, right? From our perspective, understanding what and really means, this is silly. But W is really asking, what is, give me all the expressions that are syntactically correct. There's an infinite number of expressions that are syntactically correct, even though our alpha has, well, I mean, what, 8 elements in it, and then our omega has 5 elements in it altogether. But the total number, the number of elements in W, which is the set of all the well-formed formulae, is actually infinite. Is that okay? Does everybody get a good sense of why uppercase W, which is the set of all the expressions that are syntactically correct, is actually infinite? Okay? All right. So if that is the case, what about zeta, right? Because zeta has to be useful for some reason. Okay, so what is it useful for? So what zeta does is it can quote unquote spread truthfulness inside the set W. So let me explain what I mean by that. I'll give you an example first, and then and then we can use that as an example to illustrate what I mean by that. Let's see. Okay, so I'm going to, zeta is a set of rules. So each rule can also be called a production. Okay, so there are different ways to refer to exactly the same thing. So we'll look at one specific example in this case. Um, so the format of a rule or production is always something like this. This symbol here that looks like a T that is rotated counterclockwise 90 degrees is called infers. Okay, it's infer. And we do have a set on the left-hand side, and then we have an expression on the right-hand side. So the left-hand side is a set of expressions using the Greek letters, and then the right-hand side is a single well-formed formula using the Greek letters. That's generally speaking how um, a production looks like. So I'm going to give you one example of how that works. Okay, so we'll say so what the set is representing on the left-hand side is if we have expressions that meet these requirements and they're all known to be true already at this point, then we can rearrange things a little bit to become the expression on the right-hand side, and that expression would also be marked as quote-unquote true. In other words, we're trying to specify rules to spread the truthfulness of well-formed formulae in the set W. We doing okay so far? Okay, so once we have an example, I think you guys will understand what that means. Okay, so now we have to be careful because each production has to make sense to us. We'll talk about what happens when it does not make sense, but for now we're going to try stuff that does make sense to us. So we'll go ahead and say, okay, easy peasy. So we'll say, if we have a well-formed formula that is using the placeholder of theta, and we have another well-formed formula using the placeholder of phi, if both of these are known to be true, now remember, these are just placeholders. Okay, they're placeholders to basically say, oh, we just need theta to be one of the things that is known to be true at this point. We only need phi to be one of the things that is also known to be true at this point of time. Okay? Then we infer that this expression can also be marked as true. All right? Remember, this is just a rule, okay? It's syntactic, okay? It is completely syntactic. All right, so let's just say that this is the only rule that we have in this propositional logic system, okay? At least for now. And given what we have already defined, which is iota starts with 1, not 0, p implies q, q implies not q or r, how do we apply this? Remember what they do. They're just placeholders. So whenever we try to apply a production, what we're doing is, okay, let's look at this pattern here. But this is hardly a pattern. It simply means give me any well-formed formula that is known to be true. That can be your theta. That's easy. 1 can be theta, right? Because 1 is in iota. Is that okay? So now we are instantiating and say, we can pick one over here. Pick me something else that is also in iota so that we can use that to instantiate phi. You guys take your pick. I don't really care. Not zero, okay. So now we have chosen two well-formed formulae that are known to be true. Why are they true? Because they're in iota. Everything in iota is known to be true. Okay? What does that mean? Well, since we have met the requirement on the left-hand side, now we can quote unquote fire the rule and mark another well-formed formula as true. What well-formed formula? I'm picking up theta as 1. I'm picking up not 0 as phi. So that means at this point of time, I can now say 1 and not 0 is now also marked as true. This is how we quote unquote spread or infect well-formed formulae in the set W by truthfulness. Are we good so far? All right? You look at this and go like, that looks a little odd, but I can sort of understand. But let me give you something that looks even odder. There is such a thing. Starting with an empty set, okay? There's nothing to match. If you think this one is easy to work with, this is even easier because I have no requirement, okay? And I can say, I can say this. Oh, I do need one, sorry. I'll show you one that does not need anything. This one is easy because all I'm saying is, find me a well-formed formula that is known to be true at this point. So that well-formed formula doesn't have to be in iota. It can be derived by the application of another another production. So all this is saying is, give me a well-formed formula that is known to be true at this point, and that is going to be also true, which is a specialization of the rule before, except this one just looks for one single pattern. Now, let me look at something that is even odder, because this one says you don't have to match anything. It's basically saying, give me any well-formed formula. Doesn't even have to be true at all, okay? Give me any well-formed formula, and so that I can say that well-formed formula or the negation of that same well-formed formula, that is true. Does that make sense to you?
So on the left side, it takes elements of I. On the right side, it gives you elements of W.
No, not quite. The left-hand side can be instantiated by anything that is known to be true at this point. So it doesn't have to be coming from iota, because it can also be derived by earlier applications of the transformations.
Okay.
Like this guy here. So once I have shown that 1 and not 0 is not only a well-formed formula, but it is also true because of the application of this rule, I could apply that here. I can now say, 1 and not false, and 1 and not false is also known to be true now. So it's not a given, it can be derived. It doesn't have to be given. Is that okay?
Kind of.
Kind of? You can think of a transformation rule as in pathogen. And the universe of all the well-formed formulae is a universe of cockroaches. The cockroaches in iota, those are the first ones that got infected as quote unquote true. The pathogens would then allow the cockroaches to infect each other. And the question is, how far does the infection go? Does it get to the cockroach that you want to be infected? I know that's a horrible analogy because you guys will walk out of this classroom only remembering cockroaches, but not exactly how it is applied in the analogy. But that is basically what it is. The transformation rules are pathogens. They are basically transmission vectors of saying, hey, this cockroach is already infected. By what way can it infect other cockroaches? Are we good so far? Kind of okay? If you guys are kind of squirmy about your cockroaches, I can choose something else, like rats or mice, humans. Yeah, that's a good one. Is that okay? So now you can have all the rules that actually correspond to what we understand, as logic. So um, I'll give you a list of those things. There's no need to memorize all of those things, by the way, because that is not the focus of this class. So let me see if I can get back to here. I think I might have a link to. All right. Okay, that's Boolean algebra. So for every single rule in Boolean algebra, you can kind of think that there is a well-formed formula associated with it. Is that okay? Let's think about commutative, okay? So we'll go ahead and go back to Zernal and look at commutative. So commutative basically means if you switch the right-hand side with the left-hand side, it still means the same thing. Very simple stuff, right? So the way we specify commutative is to say, give me something that is known to be using a conjunction. So we'll focus on conjunction first. Okay, so I'm going to pause right here. So this time I'm looking for one single well-formed formula that is true at this point. But it cannot be just any well-formed formula because it has to be something and something. In other words, the conjunction has to be the last operator of the entire well-formed formula. I don't really care if theta is gigantic, has its own gigantic expression, or whether phi has its own gigantic expression. All I really care is the last operator of this expression is a conjunction. Is that okay? I'm looking for a pattern. So now I can say, hey, if that is known to be true at this point, then this is also known to be true. So this expresses the commutative law of conjunction. Are we doing okay now? I mean, kind of getting an idea of how to apply this. So using this, knowing that 1 and not 0 is a true well-formed formula. So now I can look at this, and then we can now instantiate and say, okay, that meets the pattern because the last operator of 1 and not 0 is an and, right? And it is true. So now you can break that apart so that theta is getting the 1, and then phi is getting the not 0. Now we reapply those placeholders on the other side so that phi is the not 0, and then theta is the 1. So that means at this point, we also mark that not 0 and 1 is also true. Are we doing okay so far? Okay? Yep.
So when you say true, it means it's a well-formed formula, right?
No.
No.
When I say true, it means it is true. So we only have certain well-formed formulae that are initialized, quote unquote, initialized to be true to begin with, and those are the ones in iota.
Okay, I have a specific question about the empty set. infers
Uh-huh.
theta and not theta.
Yep.
So for all, that means for all sets of iota, there is an empty set
No,
production.
no. That's not what it's saying. It is saying there's no requirement whatsoever. There's no requirement about theta. You can pick any well-formed formula as theta, and this would still be true. The left-hand side is trying to specify a pattern, so that it's a constraint of what is applicable. What qualifies this rule or transformation to fire. This requires that we have well-formed formulae. These two can be the same, okay, but they don't have to be. But we need well-formed formulae of these two to begin with. Then we can say this and that theta and phi is true.
And we choose what's on the right side of that expression, right? We choose what the rule is for those two that requirement.
Well, if you can meet the requirement on the left-hand side of the infer symbol, and you can say, oh, I can find something that is true, and I can also find something that is true to instantiate these two, then you will qualify to fire the rule. You're qualified to transform. The transformation is simply saying, oh, okay, so now that we know this thing, that's using the placeholder of theta, and this thing using the placeholder of phi, we know those things are true. That means, I can now also mark another well-formed formula in the form of 1 and not 0 in this case to be true. Yep.
So if you made the empty set the first statement,
Mhm.
what would would
So-
be empty?
So the empty set is simply saying there's no requirement. There's no constraint as to what theta has to be in this case. There's no constraint on theta other than it has to be well formed.
But the answer you gave on the right side is based on what you said above, right?
You
The
mean-
format, meaning theta not zero.
Okay, so you're talking about. Okay, let me move my mouse cursor. You're talking about this?
Yeah, that statement or that the right side of it is because of what you said.
Nope. No, this is all by itself. This is just syntactically saying that, give me any well-formed formula, doesn't even have to be true, but that thing or the negation of itself is true. That is basically what it's saying. Yep.
And you're choosing for this logic system the right-hand side of that inferation, right? Or
Whatever is inferred on the right-hand side.
Yep.
Whatever is being inferred. Yep. So the left-hand side is a constraint. It is basically asking what kind of cockroaches are we looking for? Okay, because you're looking for some infected cockroaches to begin with, and we're asking, okay, what kind of cockroaches do you want? How long do you want the antennae to be? You want one missing link on one, and so on. Okay, so the left-hand side, the set, is actually trying to place constraint on what well-formed formulae, what is the format that we're looking for. The right-hand side is basically saying, okay, based on the pattern that you specify on the left-hand side, based on the placeholders, now using the very same placeholders, if there's any, we can now construct something, another well-formed formula, and then we can now say, oh, by the way, that is true also. We doing okay so far?
Good.
Yep.
So, by your first set of or production, does the theta and pi have to be two different elements, unique elements,
Nope, they don't have to be.
or just asking for two elements, right?
It's just saying, give me two.
Two, not.
Yep.
It could be one and one, and it still be satisfying the condition.
Are you talking about this one up here?
Yes.
Yeah. So with this one, there's no requirement, that they have to be the same or they have to be different. This is just saying, give me one, give me a well-formed formula. It doesn't specify the format. So it can be conjunction, can be disjunction, can be negation, can be just a simple alphabet from alpha. So it can be one, right? That's the reason why it can be one. Um, and then once you find me, a way to fill the placeholders with a well-formed, each one with a well-formed formula that is true, that is known to be true at this point, then I can conclude using the very same placeholders. Now that we know, theta is 1 and phi is not 0, because we just randomly chose something something that are true. So now we can conclude that by combining these two, this is also going to be true. Yep.
This is all arbitrary, right? This isn't necessarily useful.
Okay, to which part are you referring? Are you referring to how I chose 1 to be theta and not 0 to be phi? Or are you referring to the right-hand side of the transformation?
The
Like,
right-hand side.
the right-hand side?
That is arbitrary.
Oh, no, they are not arbitrary. These are reflecting actual logic.
Okay.
These are actually reflecting actual logic, because if you know that theta is true and you also know that phi is true, I think you can confirm the conjunction of those two has to be true too. So each transformation rule should, okay, not necessarily the case, but it should reflect a Boolean algebra rule that we actually use when we have to derive stuff.
Okay, but it could make the right side not reflect logic. And
Then you have a useless system, nonetheless, a system.
Thank you.
Mm-hmm. So everything that we're talking about here has no inherent meaning associated with the symbols. I just chose the transformation rules to reflect what we actually use as humans. We good so far? All right. So you can probably imagine there are a lot of these rules, because every single rule in Boolean algebra transforms, not, I shouldn't use the word transforms, has an equivalent production matching it. So there's a whole bunch. But that's not even the problem. There are two problems here. One problem is W, which is the set of all the well-formed formulae, is an infinite set. It has an infinite number of elements. That is why we have a haystack that is infinitely large. All right? The second problem is, but which transformation rule am I supposed to use? Because as you can see, we can keep using the useless ones over and over again, and it ends up with something that is not particularly useful. We end up with R and, well, I mean, in this particular case, we can end up with, okay, 1 is known to be true. So now, using the first rule, okay, this is getting harder for me to do because I have to move the mouse cursor to over here. So if I know that 1 is true because it is in iota, I can now say, okay, this theta can be the 1, this phi can also be the 1. So now we end up with 1 and 1 is true, right? Okay, so now 1 is infecting 1 and 1. But now that we know 1 and 1 is true, we can also use 1 and 1 to instantiate both the theta and also the phi. So now we end up with 1 and 1 and 1 and 1 is also true. And we can keep doing this until the cows come home, or way beyond that, right? So that means I can apply these transformations. Even if we have all the useful transformations, which one are you going to choose which one are you choosing to use next? Becomes a big question. Which is the big question that you guys all have to deal with when you take Math 372 or an algebra class, or any class that requires derivation. Is, okay, we know there are a bunch of stuff that is applicable, but which one am I supposed to use? That's one question, right? That is one problem. The second problem is, when do I stop? Okay, before we talk about that, let's talk about what the problem is. Okay, now that we have a system of alphabets, operators, well-formed formulae, um, iota, which is things that are known to be true to begin with, and then transformation rules that can be used to say, if I know this is true and that is true, then we can also mark that one as true as well. So now that we have a system like this, what is the problem? The problem in this specific case is I can now pose a question. I can now say, well, what about this? Is that true or not? if you already have taken a class in logic, then you go like, yeah, we know that for sure that is true. But remember, the um, propositional logic system is completely syntactic. It has no understanding of what is implication. So what we need to do to show that P implies R is true is really to apply these rules over and over again and see if eventually we'll mark the well-formed formula expression of P implies R is true or not. Are we okay so far with what problem we are attempting to solve? So using the cockroach example or analogy, in this case, we have exactly 1, 2, 3, 4. We have 4 cockroaches that were infected when we put them into the universe. So these are patient zeros, or patients zeros, patients 0. Okay, and now we have a very specific cockroach that we want to keep an eye on. That cockroach has to be P implies R. And then we have very specific transmission methods. Okay, if this cockroach is infected and that cockroach is infected, then we can say that one is also going to be infected. Those are very specific transmission, vectors, and those are in the form of elements in zeta. So each one of these rules is basically saying we can infect cockroaches in a very specific way. We can specify the requirements. If these requirements are met, then we can infect that cockroach over there. Is that okay? In some cases, it's very specific. This cockroach needs to have an and it has to be a conjunction. In some other cases, it is not specific at all. There's no requirement. Okay, so we can start to mark this particular cockroach, doesn't matter what theta is, as infected. Are we good so far? Yep.
Why do we need Z when that proposition is made up of A and omega already? Like it has elements of.
This is one element of zeta. So zeta has elements that look like this. This is one element of zeta. This is another element of zeta. This is another element of zeta.
What I'm saying is P implies R. P and R are already in A, implies is in omega. That means they're already part of I, right? And I it means they're true.
But we do not know whether P implies R is true or not. We know it is well formed. That's all we are confirming. There are two things to each expression. One is it syntactically correct, which is it a well-formed formula? That's the first question. P implies R obviously meets that requirement because implication is in omega 2, P is in alpha, R is also in alpha, so that means P implies R is well-formed. But the second question is it true? Well, as usual, I want to go for the lazy approach and say, okay, is it in iota? Because that's the first place to look. No, it is not in iota. So that means that cockroach is not a patient 0. It is not infected to begin with. So the question is, through all of the vectors that are as elements of zeta, can we end up infecting the cockroach known as P implies R? That is the question. Okay? But the problem with this method is we don't know when to stop, because you can head out in the wrong direction, end up with something totally useless, which is what I showed earlier, which is 1 is true, so is 1 and 1, so it's 1 and 1 and 1 and 1, so is 1 and 1 and 1 and 1 and itself and so on. So you can head out in the wrong direction forever and never really touch the cockroach that we want to touch, right? So you ask, then you say, but Tech, we are smart, okay? We are not going to be so stupid to use the 1 and 1 and the 1 and 1, the whole thing and itself and so on. That is correct. But remember, we're trying to automate. We're trying so that we don't do this. We're trying to write programs to do this. So how does the program make a choice of what transformation rule to use next? At any given time, there's a whole bunch of transformation rules that are ready to fire by using different placeholders, by substituting different things as their placeholders. So you have a lot of choices at every single point of time. Which one are you going to choose? Which one is the program going to choose? You go like, well, aren't there heuristics or something like that? Can we train a neural net to do something like this? The answer is probably not. Okay? So here's the problem. The problem is we have a system that can be used to find out whether P implies R is true because of iota and because of all the transformation rules in zeta. But the problem is to actually do it is not easy. Are we getting this? Okay. So in my notes, okay, so there's still a little bit more concept to talk about, but I do want to give you the map of what we are talking about here, because once we understand the map of the whole thing, I think it becomes easier for you guys to understand the details. So what I'm proposing is let's collapse all the rules, or almost collapsing all the rules, so that we only have resolution. So what resolution looks like is this one over here. So the mouse pointer is right below basically the only rule that we need to use, and there's none other. Okay, this is all we need. That's resolution. And the thing is, we can also redefine what is well formed. And once we define what is well formed, W is no longer infinite. It is finite. So with that mechanism, it's easy to automate because one, your search space is finite. In other words, you can literally look at every single cockroach and say, should you be infected? Nope. Should you be infected? Nope. Blah, 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 and so on. But there are only so many finite cockroaches that you have to inquire, that you have to check. That's one. The second one is you don't have to choose a rule to apply to see which other cockroach to infect because there's only one rule. So I can collapse all the rules into one single rule, or just about one single rule, and it makes it very easy to automate this entire process. So that's where we're heading. What we have done today, up to this point, is to describe a system, traditional system of propositional logic, which usually end up with 20 something productions, and it's difficult to choose which one to apply next. Even if you are a seasoned mathematician, it will still take you some time to go like, okay, maybe that. No, that's not going to work out. Let's try this one over here, and so on. So we're changing the entire system into something that is fully automation capable, because of the mechanism change. Are we good so far? So let me give you we still have, how much time? We still have 3 minutes, 2 minutes or so. So let me give you a roadmap of what the next class or the next two classes will be talking about. So in the next class, hopefully we'll get to resolution. In other words, Tech, are you really sure this is going to work? Is it sound? Does it make sense, right? Because we don't want any transformation rule that doesn't make sense. So we will basically prove that if you have a disjunction like this and a disjunction like this, where one component of one disjunction is the negation of the other one, we can now get rid of that thing and just concatenate the rest of the two disjunctions. Okay, because it looks like, are we really sure this is going to work? The answer is yes, it is going to work. I don't think we can finish that next lesson because the next question is, can we use CNF or conjunctive normal form to represent every Boolean expression that can possibly be? So we look at the entire W and we ask, can we transform every single one of these into a specific format that we need in order to apply resolution? So that's the second component. The third component, yes, there's one more. The third component is proof by contradiction. So this is proof by contradiction because we are actually using a very interesting technique to prove a theorem, and it is called proof by contradiction. Now, proof by contradiction, I can give you one quick example, and that will be the last thing I talk about today. Think about the pigeonhole principle. You have more pigeons than there are pigeonholes. So when the pigeons come home in the evening, I guarantee that at least one pigeonhole is going to have more than one pigeons. Makes sense, right? But if I ask you to prove it, how are you going to prove it? Think about it, okay? So using proof by contradiction, it is a snap to prove that theorem. But if you want to use a direct proof, it's a little bit hard, okay? I have given up to use a direct proof, but proof by contradiction, which is basically negating the result and apply that to the rest of the assumptions, you should come up with what we call a contradiction, which means it cannot possibly happen. So that's kind of the roadmap of where we are going with this particular module. So I really strongly advise everyone to read ahead because there's a lot of detail. So if you read ahead, that will help you, make the connections at a higher level when you already understand the lower level concepts. All right, I'll see you guys on Wednesday.